we are ready for what I consider the fundamental seed for the entire differential calculus. So it may be the case that I have recently defined what it means to talk about the derivative of some function f at some value of x, label it a, but I haven't talked about the derivative function. So here I go. It may be the case that I had two definitions or two versions of the limit of a difference quotient for the derivative of a function f at a single value of x. Again, call it a. Here, I've only got one version. So formally, the derivative function for f evaluated at x is now formally defined to be the limit as h goes to 0 of this Newton quotient. I might even say that a function is differential if this limit exists. Typically, I'll talk about differentiability over some interval. It may be the case that what I will do next is get some practice with evaluating derivative functions, but for the brief moment, can I just play with pretty pictures? So here I have the graph of some function f, albeit at some value of x, say right here, I have a discontinuity, but it's a graph of the function. Now, what I want to do is to visually, from this graph, construct a graph of this equation. Not sure how well it's showing up, but I'm trying to draw it in blue. My red's just a little bit too light. So here I go. Notice, at this particular value of x, the slope of the tangent line to the graph of the equation y equals f of x is 0. But the slope of the tangent line to the graph of this equation at that value of x is the y value on the graph of the derivative function. So at that value of x, the y value is 0 on the graph of the derivative function. Makes a lot of sense because, again, the tangent line to my black curve at that value of x is horizontal, so its slope is equal to 0. Therefore, the y value on the graph of that equation should be 0. Now, notice that the slope of the tangent line to the graph of this black curve is equal to 0 here as well. And that too will be a y value on the graph of my blue equation. Notice how for any value of x between here and here, slopes of tangent lines to the black curve are all negative. Walking left to right, they start up slightly negative, more and more negative, less and less negative, back up to 0. Well, that's what the corresponding y values are going to do on the graph of that blue equation. Notice how to the left of that value of x, the tangent lines have slopes that are getting larger and larger and larger in the positive direction, walking backwards right to left. So walking backwards right to left, I guess the corresponding y values in the blue curve, which represents slopes of tangent lines to the black curve, are increasing. Now, as I roam from this position to this position on the x-axis, observe what the slopes of tangent lines are doing on the black curve. They're increasing from 0 up to some positive number. So the y values in the blue curve are going to increase from 0 up to some positive number. Now, I might be a little off. I never unitize my axes, so maybe it actually tops out down here instead of up there, but at least I've got the general behavior. Now, for any value of x from here to here, the slope of the tangent line to the graph of the black equation is 0. And so I guess on the graph of this equation, all the y values therefore would be equal to 0 from this position on the x-axis to this one. Notice something interesting to the right of that value of x. For the black curve, slopes of tangent lines are all constant at some negative value. So I guess I'll pick up at some negative value on the graph of that equation, continue to the right. So I think, roughly speaking, I have sketched the graph of this blue equation with the blue curve in the board. Now, notice some interesting things. On the black curve, that dot's closed. But on the blue curve, there is no corresponding point on the graph. The reason being this. There are no superscripts for the number 0. So it is understood that this is a two-sided limit. So come back, take a peek at maybe with my left finger, excuse me, my right finger, fixing that point right there with my left fingertip. Let me go ahead and move along the black curve and talk about the slopes of secant lines. They're getting more and more positive. So I expect the evaluation limit of the slopes of secant lines to be positive. But fixing my left fingertip here, my right fingertip here, moving along the curve, getting closer and closer to this point, slopes of tangent lines are all negative. Well, I misspoke. Slopes of all secant lines are all negative. And therefore, the true one-sided limit does not exist. Notice something else. At this value of x, there is a corresponding y value in the black curve, but there is no y value in the blue curve for really the same reason. Fix this point, move along the curve, talk about secant lines, slopes. They're all 0. So the left-hand limit is 0 when it comes to my formal definition on the other side of the inkboard. However, coming in from the other side, the corresponding slopes of secant lines are all negative, and therefore the two one-sided limits do not agree. Therefore, the two-sided limit doesn't agree with the definition I have on the other side of the board. And so I think this black curve is not differentiable at that value of x and that value of x, because the limit of that difference quotient, or the limit of that Newton's quotient, does not exist because two one-sided limits do not agree.